In this video, I'd like to continue talking about powers of complex numbers by looking at specific example problems. And in a previous video, we derived a formula for taking a complex number z and raising it to some exponent, which we can call n. And the way that we approach the problem is to first write our complex number z in its polar form, and it will be equal to the magnitude or the modulus of z multiplied by the cosine of the angle of z plus I times by the sine of that angle, where this angle theta is measured relative to the positive real number axes. And we will raise z to the nth power. So this entire expression gets raised to the nth power. And what we found is that this is equal to the magnitude of z raised to that nth power multiplied by the cosine of n times by our angle theta plus I times by the sine of n multiplied by that angle theta. And the way to interpret this is that when we raise our complex number to the nth power, the magnitude is multiplied by itself n times, and the angle is added to itself n times. And this also goes by the name of de Moivre's theorem, which I'll write down very quickly. And I should mention that this theorem is not only useful in finding the different powers of complex numbers, but it can also be used to generate different trig formulas that are commonly used. And that's something we will look at in a later video. But for these example problems, we essentially just need to rewrite these complex numbers in their polar form and then apply this formula. And for these problems, we are actually told what the modulus and argument of a complex number are, where remember the modulus is just another word for its magnitude or its absolute value, and the argument is another word for its angle. So we are told that the absolute value of z is equal to 6, and that the angle is 210 degrees. And so we can rewrite this complex number in its polar form as 6 multiplied by the cosine of 210 degrees plus I times by the sine of 210 degrees. Now, if we weren't told that as a hint, we can just apply the formula, since the magnitude of a complex number is just the square root of the real part squared plus the imaginary part squared. If you plot this on the complex plane, you can create a right triangle and use the Pythagorean theorem to find its modulus, its distance from the origin. And we can also use trigonometry to find the angle theta, or we can use the formula that it's equal to the inverse tangent of the imaginary part over the real part, though for this, we need to be a little bit careful, since this would actually be in quadrant 3, somewhere down there that's not drawn completely to scale. And this formula is only valid for the first and the fourth quadrants. For quadrants 2 and 3, we need to shift this angle. This formula gives an output between minus 90 degrees and 90 degrees. So to get angles over here, we would either need to add 180 degrees for quadrant 2 or subtract 180 degrees for quadrant 3. Or you can just draw the right triangle and think about it geometrically. But either way, you can find the modulus and the argument when it's not given. Now, considering that we do have the polar form of this number, we can now apply this theorem here. We can take our complex number z and we're going to raise it to the third power, and we will essentially take the modulus and raise that to the third power, and we will take the angle and multiply the angle by 3. So we get the cosine of 3 times by the 210 degree angle plus I times by sine of 3 times 210 degrees. And we just need to simplify. 6 to the third power is just 216. And for the angle, we have 3 times 210, which would be 630. And we have that for both of these angles. Now, this angle is greater than 360. So if we take our angle of 630, we can subtract 360 just to find an angle between 0 and 360 so that it's more clear where the angle is. And after subtracting, we will find a 270-degree angle, meaning that our complex number raised to this third power would be 216 multiplied by the cosine of 270 degrees plus I times by the sine of 270 degrees. And this is a special angle. If we consider the unit circle, 270 degrees would put us all the way to the negative imaginary axes. And down here, the x and y values we know. And on the unit circle, remember the x value is the cosine of the angle, and the y value is the sine of the angle. And the x value here is 0, and the y value is -1. Meaning that the cosine of 270, this is equal to 0, and the sine of 270, this is equal to -1. So when we simplify everything, let me change colors here, we get that z raised to that third power is 216 multiplied by 0 plus I times by -1, or just minus I. And when we distribute, we would just get minus 216I. And we can see that that would be choice letter B here. Now, of course, a way to check this is to take our complex number in its rectangular form and actually multiply that out 3 times. We would have 3 sets of binomials. You pair 2 of them together and you multiply those out, and then you take that new expression and multiply it by this last binomial, which again is just z, and you can verify that it does equal minus 216 times I. But of course, this method is quite tedious when z gets to higher and higher powers, which is exactly why this formula can be so useful. Since if we want to raise z to a very high power, we are just taking its magnitude and raising it to that exponent, and we're just multiplying its angle by whatever that power is.